When we get started today, Lynn Alley is going to teach you the lesson. Hannah Green is going to demonstrate the lesson. And I'm going to be the sign man. So I'll be doing little things like this. We're going to start right in with a penny for your drops.
Scientists use pipettes. You might have heard it called a dropper. It's used by scientists. You might also have seen it in medicine that you might have had at home. What word do you see at the beginning of pipette? Pipe. So it kind of looks like part of the pipette kind of looks like a little tiny pipe. E-T-T-E in French means little. So that's how pipette got its name. It's sort of a little pipe. And the trick to using a pipette is to squeeze it so gently that you can get just one drop to come out at a time. So that's part of the purpose of this lesson, to teach you the skill of pipetting, meaning that we hope when we finish, you'll be able, or at least better able than when we start, to get one drop to come out at a time. There is a correct way to load or fill your pipette. So we're going to try that. Before you even put your pipette in the water, and again, you can watch Hannah, she will show you, before you even get the pipette wet, you squeeze the bulb and you keep it squeezed. So I'd like everybody to do that. You keep it squeezed. While it's still squeezed, you put the small end of the pipette in your water. Keep it squeezed. So put it in your water with the bulb still squeezed, and then gently release your squeeze, and you'll see the water come right up in the pipette. So let's have everybody try that. I want them to squeeze the bulb, and then while they're holding the bulb, put the pipette in the liquid, and then release the bulb while the pipette's in the liquid. Don't let go of your pipette. You still need to hang on to it, but just release your squeeze. And then when you pick it up, that water should stay right in there as long as you're careful not to squeeze it again. Now what I'm going to have you do is see if you can put just one drop. See if you can hold it right over your bottle that your water's in. I want you to see if you can get just one drop to come out of your pipette and go back in the bottle. Not a squirt, just a drop. So the trick is to squeeze it very gently. See if you can get just one drop to come out. We're going to get better results on this experiment if we do one drop at a time. If you get one drop to come out, you want to try a second one? See if you can get a second one to come out, just one drop at a time. While you're finishing up your practicing, and you've seen that one little drop come out, I want you to make a guess, which scientists call a hypothesis. I want you to make a hypothesis about how many drops you think will fit on the top of your penny. Don't put any on your penny yet. Just think about that. Now, the great thing about a hypothesis, which is a scientific guess or estimate, you can't get it wrong because you're just making the best prediction that you can based on what you've learned. And what you might have learned so far is how big or small that little drop of water looks when it comes out of that pipette. So how many of those drops do you think you'll be able to put on top of that penny without it flowing off the sides of the penny. And you're going to write that hypothesis, that number, on your data sheet. Right beside penny and under hypothesis.
Right.
And again, don't worry about making a guess. It's a hypothesis. It's like an opinion. You can't get it wrong. It's just your best guess. Let me know when we're ready to go on.
I'm seeing anywhere from 1 to 7.
Okay.
3 seems like the most common answer, but
Okay.
I see 1 to 7, numbers from 1 to 7. And they all have something written as a hypothesis.
Excellent. Excellent. All right. Now, I would like everybody to put just one drop on your penny, being careful not to touch the penny with your pipette, and don't touch the water drop with your pipette after it lets go of the pipette. Let's just get one drop to start with.
1 drop, don't touch your penny with your pipette, and don't touch the water drop on your penny after you drop it.
And I'd like you to look as closely at that drop as you can and see if does it look just like a flat puddle, or does it have a shape to it?
It's like an oval circle shape.
They're saying it's like an oval kind of circlish shape.
Does it bump up off the penny a little bit?
They agree that it bumps up off the penny.
Okay, so it kind of looks like a little bubble, maybe? Okay, that shape where it sort of curves up off the penny is called a meniscus. Mrs. Haskell will show you that word. It's called a meniscus. And it does that because of the way the atoms that the water molecules are made of, the way they attract each other, almost like little magnets, kind of like little magnets. So that's called a meniscus. Would you say that with me, please? Meniscus. It's kind of a strange word with a funny spelling, but it's pronounced pretty much like it's spelled. Meniscus. Meniscus.
Did they tell you to do that?
Okay. So now what you're going to do very carefully, and you need to be especially careful not to touch the water that's already on the penny. So the trick is get the pipette as close as you can to the water that's already there and to the penny without touching either of them. And now you've got to count how many drops you can put on that penny before it starts to overflow. So you've already got 1. Don't forget to count that one. So your next penny is drop number 2. So you just go ahead, continuing to add water drop by drop until it falls off your penny. Remember to count.
I have one student saying it was like a dam, and then the dam burst and it ran off the penny on him.
Excellent. And that dam forms because of that meniscus that your first penny showed. And then you might have noticed as you added more pennies, more drops, as you added more drops, if those drops were all together and sort of kept making a larger bubble, they had a bigger meniscus. So is everybody finished with that?
Yeah.
All right, so you need to write down in the second box in the first row where it says number of drops, trial 1, you need to write down how many drops you were able to add to the penny before the dam broke. Now, if you said 8 and the dam broke, then the number of pennies that were able to stay on the drop was 7. So you're probably going to need to subtract 1 from your actual count. Does that make sense? Because we want to know how many stayed on the penny.
We got some large numbers.
Yes.
So just take 1 away, guys. It's that simple. Take 1 away from what your actual count was.
Because that last drop broke the dam. You want to know how many drops were on there before you broke, just before you broke the dam. What are some of the numbers we're getting?
I'm seeing 31, 21, 20, 16, 13, 11, 14, 18. So got some large numbers.
Okay, now, one thing that scientists attempt to do when they're doing an experiment is we call it analyzing the data, seeing if there's any kind of pattern or seeing if there are any differences. And I heard some differences. Not everyone got the same number. Can anybody think of a reason that everybody might not have gotten the same number? You all had a similar penny. You all had the same, a similar pipette. So we might call those controls or things that stay the same during an experiment. What might have been different, or as scientists say, what might have varied that would have caused you to get different numbers?
Go ahead, Con.
Like putting bigger drops and other people putting like medium and.
That's right. Not all of us are pipette exactly the same as each other, and that's okay. So if you made bigger drops, you probably aren't going to get as many drops on your penny. Now, what scientists try to do to make sure their data is as accurate or correct as it can be is they do repetitions or replicates or trials. They try it again. At DEI, with our experiments that go out in the mud, we usually try to have at least 5 replicates that are all the same as much as we can make them. I've called them trials on your data sheet. That's another word that means the same thing. I like the word trial because it reminds me we're trying it again. I also like the word replicate because a replicate means it's the same. So we try this again, trying to do it exactly the same way we did it before. So what you're going to do is you're going to dry your penny as much as you can, and then you're going to do the same thing again. See how many drops. You can try to make your drops exactly the same way you made them the first time. Remember to count. Remember not to touch the water that's already on the penny or the penny itself with the pipette. Get as close to the penny or the water that's already there as you can and carefully add those drops. So you're going to try it again and record that number. Remembering to subtract 1. If it flows over at drop 30, then you actually got 29 drops on the penny. Once you finish that one, your second trial, you'll write the number of drops in the appropriate box, dry your penny, try it again.
So you're going to do this 3 times. Just raise your hand if you need more water and I will come to you. Make sure you're recording every time. Make sure you're drying your penny.
Now, those that have finished their 3 trials, what I'd like them to do is look at their 3 numbers and compare them with each other. And if they'd like to let me know how they compare, We could talk about that. This is called analyzing the data, looking for patterns, looking for differences, see what we can learn from the data.
So did you guys notice anything about your 3 trials?
Yeah.
What,
They're
okay.
numbers.
Shh. Elin, go ahead.
I noticed if you space them out more, like if you space them out more and not put them all in the center, your number might be high.
So Elin's saying if you space the drops out further away from each other, you get a higher number than if you put the drops right on top of the other drop, their original first drop.
Okay, so you're already really kind of thinking ahead, planning a little bit different experiment. In order for this data to be as correct as possible, you would want to do it the same every time. But what you have done, you've thinking ahead already, which is something that scientists also do. After they finish an experiment, thinking, I wonder what, now that I know this, or I've tried this, I wonder what would happen if I did this. I'm also so good thinking. I'm also interested in hearing from somebody that felt like they tried to do it exactly the same every time.
Who tried to do it exactly the same? Ben?
I tried to do exactly the same, but then it kept going up, and I might have been getting a little smaller.
He said he tried to do it exactly the same each time, but his numbers did increase each time, so he's not sure that he got the same, his drop was the same size.
Oh, awesome. You're already analyzing the data. Could you share your numbers with me, please?
My first one I got 20.
Just pull your mask down, honey, and say it really
My
loud.
first one I got 20, and then my second one I got 24, and then my third one I got 31.
Interesting. Do you think there's any chance that the last time you might have skipped, like, or maybe the first 2 times you really might have been at 31 and 34? Maybe you got better at pipetting, and on the last one you were getting better at getting just the tiniest possible drop each time. And remember, at the beginning I said that was part of why we were doing this, to try to get better at pipetting. So good job. Now what would be interesting is to try, and this is why I think why we generally do 5 trials or 5 replicates at DEI. If you have 2 that are pretty close together and 1 that's quite different. If you did 5 and you had 4 that were near 21, and then that 1 that was 31, we'd call that 31 an outlier. Something maybe went wrong, we're not sure what. But we can't really say right now it's an outlier, because maybe if you did 2 more, they'd be closer to 31. Okay, but this is what we're doing, beginning to analyze the data. Mrs. Buskett, are there other pieces of data we should discuss, or shall we move on?
I think we're good to move on right now.
All right. Another thing that you can do with this, if you have more time and your drops, your drops are fairly consistent across the row, you could add another column to your table that says average number of drops. Okay. All right. But for now, let's go to the nickel. But before you put any water drops on it, I want you to make a hypothesis. You have an idea at this point how many drops could fit on your penny. So this hypothesis you might be a little closer. You see how many fit on a penny. So now based on that, make a hypothesis about how many drops you think will fit on the nickel.
Is it all right if they go ahead and try to do the nickel now?
Absolutely. Remember not to touch your nickel or your drops that are already on the nickel with your pipette, but get as close as you can because you don't want it to splash down there too hard because that would actually break your meniscus that's already on the drop that's on the nickel.
They all have their first trial for their nickel done.
Okay, so we're going to analyze the data again, or begin to. We'll do it again once you've got the second and third trial done. But how does this first amount compare with your drops you got on your penny?
So how did it compare from the penny to this one?
It was a lot like bigger and like size.
A lot more drops
Yeah.
were needed for the nickel, they're saying.
Yeah, and why would that be?
Because the nickel's bigger than the dime.
That's right. That's right. Okay, so do your 2 more trials for your nickel. Again, trying to do it exactly the same way. The object is to get as close to that first number for trial 1 as you can. But again, if you're still learning to get the smallest drop you can, to keep those drops the same, that number could change. That's okay too. I will update this so you'll get a new data table with a place for 5 trials and a place for the average.
That would be great, because I will continue with this activity tomorrow as well.
Excellent. As students finish with their 3 trials for their nickel, I'd be interested to hear from some of them how these numbers compare to each other. Were your drops for your nickel closer together than your drops for your penny, or were they, still spread out, or how's it looking?
Okay, so continue on, make sure you get all your trials done, and then we'll talk about your data.
And remember to dry your nickel between each trial.
Some of the students are being very meticulous about size of drops. They're really taking their time.
That's very good. Has anyone finished their 3 trials for the nickel?
Yeah.
Do you want to tell me how your numbers compare to each other just for the nickel?
The first trial, I got 26. The second trial, I got 56. In the third trial, I got 43.
That's quite a range, quite a big difference in those numbers. Do you have any idea maybe why the numbers are so different from each other?
Maybe because the first time I was trying to make bigger drops, and it was on a different side than the other 2.
I think that's probably a good guess.
So he flipped his nickel and did
Ooh,
2 different
interesting. All right, so did he flip his nickel after his first trial?
Yes.
Yes.
All right, tell me the numbers again, please.
The first one was 26, the second one was 56, and the third one was 43.
Okay, so that kind of makes sense. And again, scientists do try different things, but for their first experiment, whatever they're doing, you want to try to keep as many things the same as you can. Okay, so that would make a difference. That's why it's called a replicate. A replicate is like an identical twin, kind of. You're trying to do it exactly the same.
I thought that was called a duplicate.
Same replicate, duplicate, basically the same.
Yes, those are synonyms. Mean the same thing.
So maybe next time, don't flip your coin. Leave it on the same side for all 3 trials.
Yes, and just see how close they come out to each other. Because that also gives you and your teacher and us at DEI an idea of, if your pipetting skills are improving, which is part of what we're trying to do here. We're trying to teach you some scientific terms or vocabulary words, but we're all, and how to do an experiment. But we're also trying to help you learn the skill of pipetting. I think that's about all we have time for today, Mrs. Buskett, if you need time for pickup. But I want to thank you. You kids are wonderfully attentive. That's a great compliment to you and to your teacher.
We will continue with this activity on Wednesday. We'll continue with the dime and the quarter, and I think I will have them do it 5 times, and then I will show them how to find the average.
Okay, great, great. Can you get a sense, just a quick sense from them, Mrs. Buskett, if they liked doing this?
They're all saying they enjoyed it.
Okay, good.
I would love to have them tell us what they found out when they practiced again and try to make sure that they did it the same way every time. That's so important. And I was very happy that they came up with the word duplicate what they were doing. And then they understand that that's what a scientist tries to do.
I agree. And a lot of the things that some of the students mentioned, like about flipping their coin over and trying to do both sides, and their observations about the different sizes of the drops, those were things that I was noticing as I was doing it here too. So I'm glad that we were both thinking the same things and getting the same sorts of results. That's always nice to hear.
A couple things, they're all seated on the floor and it's dark so we can see the screen. So those might have also played into some of our results, that they're not at an actual desk where, they're bent over. There are a lot of different things going on. So it should be interesting to see what the results are tomorrow when we're at our own desk and we have less, we can see better.
It will be. Yeah, very much so. Thank you so much for letting us come into your classroom